Hi, I've decided to show you problem number 32 in chapter 5, page 152. Now, I originally have a system of blocks that are set up similar to this. The 5 kilogram block is a little bit lower than the 15 kilogram block, but I'm holding them steady. Because I'm holding them steady, the initial velocity of each of the blocks is 0. My final velocity is what I'm trying to find. Now, what do I mean by final velocity? Well, I let the 15 kilogram block go. It's going to move downward. They want the velocity when it's moved downward 4 meters. That means its change in height is negative 4 meters. Now, if it goes down 4 meters, the 5 kilogram block will be pulled up 4 meters. So that will change the potential energy of both the 15 kilogram block and the 5 kilogram block. And we're using energy techniques to solve this problem. On the other hand, the 10 kilogram block isn't going to have its potential energy changed at all because it experiences no change in height. Now, in this problem, there are no dissipative forces, there's no friction, so they're only conservative forces. Well, what do we know about conservative forces? We know total mechanical energy is conserved. So the total initial mechanical energy equals the total final mechanical energy. And I've written an equation here. I've written the potential energy for each block initially, initial for 1, initial for 2, etc. I've also written the kinetic energy, but as you see here, I show that it goes to 0, and you should do it this way on the AP test. Put the kinetic energy in, show it goes to 0. That equals the total final potential energy of all 3 blocks plus the kinetic energy of all 3 blocks. Okay, now what I'm going to do is I'm going to subtract the initial potential energies from both sides of the equation. So on the left side of the equation I have 0. On the right I have the final minus the initial for each of the 3 blocks. So I've written that. And I still have final kinetic energy for each of the blocks, but each of the blocks is moving at the same final velocity because if they did not, the strings would either become very tight or very loose. So I've just written V sub F for each of their final velocities. Okay, now I know the potential energy of block number 2 does not change. So again, I show this goes to 0. Now it's time to put in numbers. Oh, nope. I factored something out first. I factored out a 1/2 VF squared from each of the kinetic energies. So I've really simplified the equation a great deal, and what I'm trying to find is V sub F. So now I'm putting in the formula for potential energy. That's mg, and it's a change in potential energy, so it's delta H. I've done that for each of the blocks. We're going to find V sub F. Now, block 1 is 5 kilograms, acceleration due to gravity 9.81. It goes up 4 meters, so you put a positive 4 there. Block 3, on the other hand, of 15 kilograms, 9.81 is the acceleration due to gravity, goes down 4 meters, so you put in a negative number there. Plus 1/2 V squared, and I just substitute the masses. Now, what I've done is I've just combined the first 2 terms to get negative 392.4, and I've multiplied 1/2 times the sum of the mass. I have 5 plus 10 plus 15, that's 30. Half of 30 is 50. And when I solve this, I get a velocity of 5.11 meters per second, and that's what it said in the book. So it looks like we're good. Hope this helped.